So I'm going to be talking to you today about human-machine teaming. And I think this is pertinent for the test community because you guys are going to be the ones that help really understand how to build appropriate expectations with technologies. And at the end of the day, I think there's kind of two things I want you to take away from this talk. One, how do we build those appropriate expectations of technologies? This is critical, especially as we build new AI systems and bring those online. Secondly, I want you to leave with the idea that human-machine teaming is all about flexibility, right? How do we engineer that flexibility? How do we test that flexibility? How do we measure that flexibility? Those are some of the things that we'll be thinking about. So overall, this is going to be kind of a 30,000-foot view of human-machine teaming. What I hope to do is leave you with a sense of how does the Air Force approach human-machine teaming? I'm going to give you some examples of some projects we're working on, and I'll talk about some of the challenges in this space, particularly as they relate to test and evaluation. But let's start with some background. We live in some really cool times, right? I'm sure all of us can agree that from a technology standpoint, it's a really exciting time. Let me just move this up a little bit. There are new technologies coming online every day. Things are changing constantly. We're imbued with new things that potentially add value, right? So the DoD has been talking about the implementation of autonomy for a long time. We've recently been thinking about things like ethics and how do we bring ethics into the mix, because some of these technologies may be delegated some authorities that are pretty important. So we need to consider those ethical elements as well. We've seen in the literature that things like generative AI tools can actually have a positive impact on employees in particular situations. Now, I'm a little bit skeptical on some of the Gen AI stuff, but I think that there are situations where they can add some good value. We've seen in the Air Force, the Secretary of the Aircraft flew on an AI-enabled aircraft. That's what's depicted here in the Vista aircraft that's out at Edwards Air Force Base. So exciting times, right? Lots of new tools, lots of new technology. But at the end of the day, it's really their interactions with the humans that's where we're going to gain the most value. And from an AFRL perspective, we've really tried to think about how are we going to glean these technologies to augment and accelerate our humans, our warfighters, our airmen, and our guardians, because we're supporting two services, the Space Force and the Air Force. And we've really tried to push the notion of decision superiority. So we want to use human-machine teams to facilitate decision superiority, making our airmen and our guardians able to make decisions faster, considering a broader range of information. Having greater resilience because we know information is going to change and there's going to be efforts upon our adversaries to make our information, let's say, less usable, perhaps less trustworthy. So we need resilience in that sense. Now, also thinking about optionality. Optionality gives us better capabilities because it gives us flexibility again. So this is where some of the flexibility comes into play. And we view decision superiority as really our way of outpacing and outmatching our adversaries' OODA loops. So getting ahead of their decision cycles, potentially breaking their decision cycles, and accelerating our own. So that's kind of the high-level view that we're trying to take with regard to how we approach human-machine teams. But academically, human-machine teaming is not necessarily a new topic. This is a topic in the literature that's been around for a while. There's lots of published papers on this topic. It's a growing literature for sure. But what is it from an academic standpoint? Essentially, it's humans and machines working together in a task context. Generally, there's roles within this task. So you have a team, and those team members have certain roles in the task. There's some degree of self-governance or autonomy, because have you ever worked on a team with somebody and they didn't have any control over anything? They're not really a teammate, really. It's more of a process. So some degree of agency or autonomy is kind of assumed with a team member. There's going to be team-focused behaviors, goals, and communications, right? When you're working together as a team, you talk about how you're doing. You back each other up. You have team process that works to support team goals, and you talk about those goals, right? That's what being part of a team really means. And ultimately, you want to get to a point where there's shared mental models. You all know what you're doing. You know what resources you have to bring to bear on a problem. You know which circumstances or contexts you're dealing with. You're all kind of on the same page, so there's synchrony. And at the end of the day, there's shared intent. So that's kind of an academic definition of what a human-machine team is. Back in 2021, some colleagues and myself, we did a review paper on human autonomy teaming, and we tried to classify the literature according to three things. We tried to look at, well, what are the things that drive teaming perception? So basically, what makes a person think a technology is more like a teammate versus a tool? Those sorts of things. We've looked at literature that tries to substitute machines for humans. So in this case, you could think of like a training environment where you have a synthetic teammate that's now standing in for one of your humans. So imagine, like, for example, in the Air Force, fighter pilots, right? Fighter pilots are pretty rare, they're really busy, and it's really expensive to have fighter pilots be part of training, right? So what if you could substitute a machine to play that role in a war game, right? Those are some things that you could do from that perspective. And finally, there's studies that look at the impact of these machines on the team as a whole. So how does the introduction of this teammate shape cohesion, shape stress, shape trust, those sorts of things? So there's kind of those three distinctions within the literature currently. And we identified a number of challenges. So some of the big challenges within human-machine teaming, how do you signal intent? So if you're a human working with a machine partner, how do you make sure that machine understands what your goals are and how those goals might change over time dynamically? That's a pretty big issue. Things like performance optimization. How do you get the best, squeeze the best out of it, right? Get the most performance benefits out of these things. Things like shared accountability, which is kind of a questionable thing. How do you get a machine to feel more accountable for what's going on? A lot of this probably has to do with traceability back to decision making, to be able to trace back what happened and why, right? And ultimately, and this is why I'm excited to talk about this for the test community, is joint human AI training. I think this is a huge opportunity. This is something that human training has accelerated performance for a long time, for decades. We need to start thinking about human machine training in similar ways to think about how can we get the right experiences so that we build the right expectations of our human machine teams. From an AFRL standpoint, how are we viewing human machine teaming? We like to think about 5 pillars of activity that we're engaging in science in each of these pillars. At the top, we have information analysis and acquisition. So here, imagine you're using AI to help parse off the world, help queue for certain things that you might want to look at, help maybe fuse data for you and analyze data for you. So that's kind of one way to think about human-machine teaming. But once you've done that analysis, you've got to do something about it. And so we provide decision support tools so that we have optionality. We can give people options based on that information that they've just analyzed. We have human-machine interfaces that allow flexible, delegated, and bounded authorities. So at the end of the day, humans are the ones that have the power. Machines don't have power. We give power to machines, right? Machines don't give power to us. So we need the right human-machine interfaces that allow that navigation to occur. And there may be times where we can delegate more bounded authority to machines, but we need to have the flexibility to take it back when it's necessary. That's a really important element. As we move along, we think about responsible use of AI. So we'll talk about this in detail in a while, but I really don't like the idea of delegating ethics to machines. Rather, I like to talk about responsible use of AI. That puts the human front and center in that whole equation. We need to be thinking about how we're using these tools effectively, and are we using them in ways that are consistent, not divergent from our value structures. And finally, kind of an interesting area is individual and team state data. There's tons of data that we have within our bodies and within teams that we can use to maybe get the machines to know more about us. Maybe know more about our workload state, maybe our boredom state, right? If we're completely bored, maybe we need a little bit more task. If we're completely overwhelmed and overworked, we probably need to shed some tasks, right? So there's lots of information that we can use to get those machines in better synchrony with us as people. Also at the team level, there are actually metrics you can look at from a team perspective to say, hey, this team's performing great. Maybe this team over here is not performing so great. So what if our machines knew that and they could start to augment us in that sense? So we've got some work engaging in that space. And ultimately, we like to think about some of these human-machine teaming elements coming together to support decision superiority. Because at the end of the day, decision superiority is all about decision advantage. So again, you've got that information analysis, the tools coming together to fuse information for you, coupled with initiative. Because the information alone is not good enough. We need to be able to do something with the information. That's where the optionality comes into play. And we're certainly working in areas such as autonomous collaborative platforms, or what you might have heard in the news, the collaborative combat aircraft domain. So You imagine you're working with robotic systems in a combat situation. How do you delegate those authorities to those machines flexibly so that you're not shut out of that equation? You're not pressing a button and saying, okay, go off, do your thing. You have the flexibility to interact and team with those things truly. And ultimately, we know that some of our missions, some of our contexts that we're thinking about in the future are going to stress our airmen and our guardians. So how do we do this in ways that we're maximizing our knowledge of their physiology and their states so that we can get the most benefit out of these human-machine teams? And so what are some of the projects that we work on? So we work on a lot of projects, as you can imagine. AFRL is a huge organization, so we have a lot of different projects. Some of the specific things we're doing with regard to human-machine teams, we do a lot of work in ISR tools. So we do a lot of work essentially taking a human-centered design approach with analysts, understanding how they go through their analytic work, and building tools, sometimes as simple as automation, right? We can't ignore that sometimes simple is better. Everything doesn't need a fancy AI tool to maximize performance. We've gotten some really good traction out of just plain old, good old automation, which is great. So we do a lot of this work in the ISR community because anybody that's worked in the ISR community knows these folks are generally pretty overwhelmed with information. They need tools to accelerate, augment, fuse data for them. We do have tools in the Gen AI realm. One specifically is we have Nipper GPT is a new Gen AI tool that came online. I want to say it came online last year or maybe the year before that. This is a tool we have available to AFRL folks. And again, in a whole, I'm pretty skeptical of Gen AI tools, right? So I would never use them to write a paper myself or anything like that, but they do have some value. So one of the big things I really like about Gen AI tools is their RAG methods, the retrieval augmented generation tools. Those are super powerful. I mean, for those of you that have used these, you can actually upload these as trusted artifacts and then query based on those sorts of things. So imagine you're like you're looking at a tech order that's 1,000 pages of data, right? Heck, nobody can remember all that information. Why not plug that tech order into your LLM and use the retrieval methods to get specific information? You've already got a trusted artifact. So in that case, I think they're pretty powerful, right? So again, I think we just need to think about what's the right use of the tools and what are our expectations. There's utility in some of the use cases. We just have to be cautious about some of the other use cases that we're thinking about. Course of action analysis tools. We do a lot of work in this space, looking at things like multi-domain command and control. If you're bringing together airspace, cyber, non-kinetic sorts of options, how do you bring those together? How do you give people a laundry list of, here are your options? And you can maybe give them interfaces that say, not only here's your options, do you want to tweak these to get better benefit from them? That's all about optionality and teaming. That's one of the big areas that we're working in. We do a lot of work in human-machine interface design to support, again, the flexible delegation of authority. We think this is pretty important because we don't want to grant machines full authority for everything, right? There may be times where they deserve to have authority about a task, but we want to be able to be flexible about it. We want to be able to give and take as needed. We think that's going to be pretty important, especially in the DoD. We do quite a bit of work with UAS orchestration. So UAS, essentially think drones, right? How do you get from controlling one person controlling one drone to one-to-many control? That's a big area for us, and we're heavily steeped in that. I'm going to talk about a specific example in a second. And things like space autonomy. Space is kind of unique because from a test standpoint, it's not like you can just launch a satellite next week and tweak it and see how things go. It doesn't quite work that way, right? So space testing is really challenging, and I'll talk about a project there as well. Let me go ahead and go on, I think, in the interest of time. So let me talk about UAS control. So imagine you're a base defender, and you have lots of drone assets and ground assets and even surface assets under your control. How do we move from a person controlling one-to-one from one to many? So we built a platform called Impact. You have to see the name of it up there. The whole idea of Impact was to move to that one-to-many control perspective. So it was designed from the start to understand this notion of full spectrum of control. So a person has the ability to do completely manual control. They can do one drone. Let's say you want to do a surveillance ring around this building. Okay, go do your surveillance and go do that. Moving up the spectrum of autonomy, we have things like play calling we can do. So you could tell the autonomy, hey, I want to do a surveillance around this building. And the autonomy can decide which vehicles to go out and assign to those roles, and it can just execute it for you. As you move up the spectrum, we have auto-initiated plays where we've pre-designated authorities for a machine to go do something in case it detects something. So let's give an example here. Let's say that there was a security issue at the front gate of this building, right? Probably you'd want to go get eyes on that facility. Maybe you'd want a ground robot to go as a presence of deterrence to go right to the front gate and say, hey, I'm here. You probably want eyes on from above. So you can designate those things in advance and pre-delegate the authorities to do those things. This is all about flexibility, right? So this has worked out pretty well using this platform in a realistic environment that have incorporated simulated and real assets that are on the ground, the air, and the surface of the water. We've demonstrated that one person can control up to 17 assets using this platform. Now, how does that happen? It happens for a couple of reasons. One, we have vehicle autonomy. So each of the vehicles has kind of its own autonomy on it. But there's also what we call an executive layer of autonomy. This executive layer of autonomy is what allows the human to give intent broadly, and that executive autonomy translates that to the machines, to the vehicles, essentially. That allows for great flexibility and rapid response in these sorts of situations. I bring this up because I think this is a really important use case for human-machine teaming. I think this particular platform and things like it, which we're using now for multiple very applied projects, which I'm not going to go into today, but we're using this same kind of architecture and mindset to support other programs. But what makes this a good human-machine teaming platform? There's a couple things I want to think about. So one, it's a real thing. You know, there are real base defenders that have a real job. You can go talk to them about that job, and they will be very interested to tell you how it works and how it doesn't work, right? So it's a real task. It's not a fake thing. Secondly, there's interdependence. So the humans and the machines are working together in this task environment to execute this task. So there's a lot of interdependencies, a lot of interaction. When it comes to human-machine teaming, I think this interaction, the bidirectionality, is kind of a really important thing. It's kind of what makes a human-machine team a team as opposed to human-machine interaction, right? That bidirectionality is pretty important. Third, there's this interactive human-machine interface. It's designed from a human-centered perspective to be intuitive. So you don't have to sit there and learn, what does this do? What does that do? It's just kind of intuitive to them because it was designed based on their tasks, designed based on cognitive task analyses. How would you do this task, right? So there's a lot of flexibility in the interface. And again, you can have anything ranging from a very manual thing, say, hey, I want this specific asset to go specifically to this location, to, hey, I want someone to go look at this thing, to, hey, I've pre-designated in advance. If you detect this, go send someone here, right? Lots of flexibility in that sense. The autonomy backbone is pretty critical because, again, this is the executive layer of autonomy that I talked about. This allows that translation of intent to occur. That's pretty critical. And one of the things I find interesting with this platform is they've designed something called background behaviors. So you can basically, let's say you've got 20 different assets that you're controlling at a time. You can put them in specific routes or specific behaviors, and the executive autonomy will manage that background behavior for you. You can pull things off as needed. You can change the plays as needed. The executive level of autonomy adjudicates all that for you. Again, what does that give you? Flexibility. It also gives you speed to react to things. So at the end of the day, if you're thinking about moving from a one-to-many control perspective, you're probably thinking about the human as an orchestrator of things as opposed to a controller. The human's not at any one point controlling specifically 17 things all at once. They're orchestrating what's going on, right? And finally, I think from a testing standpoint, I think is really important, there's shared semantic space. So the executive autonomy knows what the vehicles are, knows what points of interest are, knows what the plays are, right? There's that shared semantic space so that there's a common understanding of what's capable, what's present in the environment. That's a pretty important assumption as well. Okay, so that's one example, and you can tell I probably like that example, right? Let's talk about some other things. So in the space domain, space is pretty hard. Everything in space wants to kill you, right? Just the environment itself, it's a hard place to operate in. So we are working on artificial intelligence tools to do a couple of things. We have this program called STARS. This is all about building autonomy to support rendezvous and proximity operations in the space domain. So imagine you've got a friendly asset out in space. Maybe it loses power or something like that. And so now maybe it's tumbling, maybe it's doing something. You're not really sure what it's doing. You need to go get other satellites to say, hey, is it damaged? Does it need something else to happen to it? So you need to go inspect this thing. You need to see what's going on. So to get our other satellites in a position where they can actually see this thing, you have to engage in rendezvous and proximity operations. And we think you can gain some benefit from using some of these artificial intelligence methods, things like reinforcement learning, to train models to go do this effectively, because it requires a lot of responsiveness, it requires a lot of speed, and some of these things are going to be hard for humans to plan very adaptively, right? So this is what this program is essentially developing and testing. We're testing the reinforcement learning algorithms that essentially do the flight operations to do the RPO. And we're also investigating another class of algorithms called runtime assurance algorithms. This is essentially setting up guardrails for the reinforcement learning tools to bound what they can do and to keep them within safe boundaries. So imagine there's these two forms of artificial intelligence. And the third element, which is what I'm involved in, is building the human-machine interfaces that allow for directability and transparency. So we want our guardians, in this case, to have control over these things. We want them to have situational awareness over these tools. We want them to be able to flexibly and dynamically interact with these technologies. And so what we did is we built a set of concept interfaces that allow not only the rapid evaluation and comparison of reinforcement learning models. So imagine, okay, you got your mission. Which model are you going to choose? So choosing a reinforcement learning model could depend on a lot of different things. We gave them a really rapid capability to evaluate based on past performance, of course. It's not based on their current performance, because that's just way too hard to do at the moment. But based on past performance of the models, these are the things you could do or select from a model standpoint that have the best performance. Really quick observations, because at the end of the day, the model you select might depend on a number of factors. You might want a very conservative model that conserves delta V, or their fuel, at the utmost. You might want a model that's more aggressive, that maybe cares a little less about the delta V, but cares more about how fast it gets done, right? And those priorities, those goals could change pretty quickly. So these kinds of tools give you optionality to make a selection pretty quick. And also we give them directability. So we give them control over how they set the runtime assurance parameters. This is that guardrail algorithm, essentially. We allow them to say, okay, how much fuel do you want to use? What's your safe limits for fuel? Because, you know, I don't know how many of you have worked in the space community or not, but fuel is a number one consideration for space, right? They don't get their refuel, at least not currently, right? So what they go up with is what they've got. So understanding fuel is a really important thing. But there's also lots of other things, like how close do you want to get? How far away do you want to get? How fast do you want to go? Because if you go too fast and you have too much rotation, that could actually damage your aircraft as well. So there's lots of things to consider in the space domain that we don't readily think about if we're focused on air operations. Okay, so bottom line here, optionality and directability. Those are two of the big things we're trying to promote with this program. Other things for us to think about. So from a human state sensing perspective, we have this program called the Integrated Cockpit Sensing Program. This is a program for fighter aircraft to essentially build sensors of the human, right? Currently, there are very few sensors for the human on fighter aircraft. There's tons of sensors on the platform. You can tell just about anything you want about the platform. You can't really tell much about the human at the current moment. So this program was built to understand things like, in particular, safety issues. So incapacitation. So those of you that know fighter communities know things like gravity-induced loss of consciousness, or GLOC, is a real issue, right? So can we build sensors that not only can detect an incapacitation issue, but might be able to get predictive about it? So imagine if you could forecast a GLOC 30 seconds before it happens, or maybe not 30, but maybe 10 seconds, right? So these are things we want to try to get after and push into the environment. And so this is a program that's got several flight hours on the F-16. Folks have been pretty happy with how it's performing, but we're moving it towards, it was designed for kind of a safety orientation. We're trying to see if we can pull additional juice out of it, from the sense of, can we get more information from a cognitive state standpoint by leveraging these really mature sensors that are in the aircraft. So can we learn about cognitive workload? Can we learn about other complex things like that? Believe it or not, that's really hard to do in a fighter aircraft. It's easy to do if you're sitting behind a computer screen and you're never moving, you never have G's, and you're never under threat for real. In a fighter, it's all different. So that's a pretty complicated thing, but we're trying to get after it because it's one of those things. I think if we can nail that down, we're going to get some benefit from that. Other things we're doing on the bottom. So we have a thing called the Focus app. This is all about understanding fatigue. So those of you that know, have been following things in the Department of Defense, some of the missions that we envision having to do might last a considerably long time. Imagine flying an aircraft for 10 hours and then engaging in the risky part of the mission, right? These are long duration missions that are going to stress the airmen that are doing it, and we need better ways to understand fatigue and how fatigue manifests in performance over the long term. So we built this app called the Focus app, which does real-time monitoring, but also pulls in some of your self-report and some of your sleep-related metrics and builds predictions. It builds predictions that allow you to make decisions about your unit and about individuals from a fatigue standpoint. This could be hugely important for the long-duration mission sorts of perspectives. And finally, we're doing lots of work in the area of autonomous collaborative platforms. These are our systems that are going to be essentially going into combat with us. We want to understand how many of these platforms can a person reasonably control? What are the nuances for mission parameters that might change? What are the nuances for things like heterogeneity? What happens if you got 10 things that are all the same or 10 things that are all different and you have to go into a mission with those things? Those are some of the questions that we're building empirical data sets for to support some of our more applied customers. And we're building at the same time workload models that can be predictive so that when we don't have the opportunity for real-time data collects, we can build these predictive models that they might be able to use to get some insight as to what they might be able to expect in certain kind of ConOps. One other quick technology I wanted to talk about is the just-in-time multi-mission airman perspective. So imagine you're a security forces guy, right, or gal, and you're put on Island X, and you're out there and you're guarding that island. Okay, well, aircraft lands, and now you got to do something different. You've got to refuel that aircraft. Well, wait a minute. I was never trained to do that. Okay, no problem. We can give you real-time information and tools to show you in real time how to do those things. Now, are you going to be able to do this for everything? Probably not. But maybe your lower complexity kind of tasks, you could give real-time information to give those training aids at the moment's notice. And we actually demonstrated the ability to take security forces folks and train them up on how to do hot pitting, which is essentially refueling while the aircraft is running. We demonstrated this effectively in a recent exercise. So bottom line here is real-time knowledge delivered to the point of need, essentially. Now I'm going to kind of back up a little bit and talk about some of the other ethical related issues. So responsible use of AI. I mentioned early on, I really don't think we should delegate ethics to machines. I know there's a lot of academic literature in this space. A lot of it's looking at ethical AI or responsible AI, all these. I don't have any problems with the terms, but I think from a DoD standpoint, we need to think more about responsible use of AI. How are people using these tools? Are they using these tools effectively in ways that are consistent with our values? And so if we can't delegate ethics to AI, which again, I want to caveat, I think there's need for science in this space because I think technology is constantly changing. And when it gets to a point where it can truly understand context of people's needs, maybe I'll change my mind. Maybe some of you will help change my mind. That'd be awesome because I love to be surprised and I love to have my mind changed on things like this. But I think right now, where things are at, I don't think we should do that. But what are we left with? So I think there's 5 things we can do as practitioners and designers to really implement responsible use of AI. So we can educate people. Common AI literacy, right, is still a bit of a problem for our communities. Do they even know how these tools work at a basic level? Do they have the right expectations at a basic level? That's something we need to do. We can think about training data. We can treat training data as a learning affordance. So what sorts of data did it train on? How recent was it? What's the breadth of coverage that it has? These can be metadata sorts of tags that we could use to essentially have better learning affordances about our AI tools and their training. Human-centered design is something I would advocate for in general. I think it's important to know how people use tools and design them in ways that are consistent with that use and not divergent from that use. Guardrails. We can create guardrails for our tools, whether they're Gen AI tools or more vehicle-based algorithms, right? So what are the bounds we want to create to allow these things to operate? And finally, I talk about joint human AI training. We need sandboxes. We need opportunities to build experience. We need opportunities to build appropriate expectations. That's what this is all about. And I think that's a huge area, and I think that's one of the biggest areas I think we need to get after as a community, is that training piece. So how would we apply this to essentially test and evaluation, right? So again, I think from an AI understanding standpoint, it boils down to things like, can you trace logic back to a decision? Can you trace a behavior back to a decision logic, right? Do you have that traceability from a test standpoint? Do you have the understandability? Do you even know how it works? And do you have control over it? These are some of the things I would think about from an AI perspective there. Talk about the data sets. So how suitable is this data set for that application, right? Are there limitations you want to note? So document that. Document your intended use of these tools in the context of their training data. Are you building infrastructure for future use? This is kind of an interesting thing. We collect so much data. How much of that data do we structure in ways that, I think in a year, somebody else might benefit from that? There might be things we can do in that space to help the whole community, right? I think that's huge. We started using terms like AI-ready data sets within AFRL. So this is, I think, going to be a pretty big issue because, let's face it, the future is probably going to want to ingest a lot of that data. So we need to start thinking about that stuff now. Scenario design. I think the training elements are so critical because this is what's going to expose us to novel situations. We want to test the edge cases. Heather got up here and talked about the edge cases. That's where the sweet stuff's at. We can't sit here and focus on nominal conditions because, let's face it, it's pretty easy to build a reliable tool if nothing ever goes wrong. It's when things go wrong, that's where we want to understand and calibrate our expectations. That's where we're going to get the benefit for human-machine teams, when things go wrong. That's why we need flexibility, right? Test beds and sandboxes, this is the affordances that give us these opportunities. We need the right test beds. How much fidelity do you need? This is an ongoing question in many communities. Unfortunately, I think the answer is you'll know when enough is enough, because your operators are going to tell you this is high fidelity enough for me to get something good out of it. Does everything need to be absolutely super high fidelity? Probably not. Does everything, but you probably need some things that are, right? So it becomes more of a discussion with who's going to use it to say, hey, is this an appropriate context to study these things? I think many times, and I know I've seen this in the Air Force, we get wrapped up in making sure everything's so high fidelity. Well, that eats your lunch from resources, time, personnel. It's so hard to make everything super high fidelity. So we got to ask the question, what's good enough, right? And finally, I just put a plug in, we got to keep collecting data. Once things pass out of the quote end of test, I know in the Air Force we have a specific thing, okay, it's no longer in test. Why do we stop collecting data on that? And there's so much to learn, especially as technology not only changes, but it refreshes. Our new tools that are coming online are going to have lots of changes that refresh down the road. We got to constantly be collecting data. We need to constantly have the metrics in place to get the information we need after test, quote, test is done. I don't think test is probably ever really, quote, done. Even though on a process map, you could probably say, okay, test is, no. I think at the end of the day, we need to continue to collect data to see how these things are doing in the field, because we're going to learn a lot, right? Human-machine teaming applied to training and education. This is kind of a slide I had in the slide deck, kind of focused on the educational elements of this. So, of course, we need on-demand tactical readiness for our wargaming and our on-demand aids. That's kind of, I think that's kind of intuitive. We're also doing work in how to accelerate learning. So there's actually some somewhat novel research showing that some of the stimulation effects, so stimulating the vagus nerve, for example, actually shows some retention benefits. So we're exploring that. We're watching how those things unfold in the field to see what we can benefit and take advantage of from that sense. If we can improve learning and increase the rate, why not? That's value added. Human performance modeling. We do a lot of modeling work in AFRL to understand things like learning rates, learning decay. How should you structure training? How should you implement that training in terms of mix of high fidelity versus low fidelity kinds of platforms? So that's work that we're heavily engaged in as well. And one of the more higher risk things that we're looking at is co-learning. How do you get humans and machines to learn together? How do you get the machine to understand the, let's say, the expertise level of a user and then adapt to that? Kind of like the intelligent tutoring of the past, but with more modern day tools. How can we get synchrony? And I think some of this boils down to things like personalization. We can tweak these to meet our personalized needs. But I think also there's an adaptability element to it. So machines that adapt to us, we actually tend to trust more, right? So there could be some interesting things there. Well, I kind of view this as more of a longer term sort of research area. And I think the last thing I wanted to talk about, because you opened up with a little bit of trust background, is any of you that know me know I've done a bit of work in the area of trust. And one of the things that recently came up for me was somebody asked, we've got the technology readiness levels, we've got human readiness levels, we've got material readiness levels. Should we have trust readiness levels? I'm like, what would that look like? And so I'm not saying this is 100% right, but when I was asked this question, we put together this paper to kind of highlight what that could be. And when I was thinking about this, there were a couple things that came to my mind. One thing was you'd want to talk about reliability, but you'd also want to talk about things like transparency or understanding. That's so fundamental to trust. I've seen firsthand, I'm not going to say specifically which group, but very relevant user groups downplay performance benefits. They would choose a less performant agent because it could understand it better than a performing agent that was better that they didn't understand, right? Transparency matters. Understanding matters, right? So that was one of the big things I wanted to put into this. Also, the perspective of different perspectives. So you've got designers, testers, users. You've got the community of users that's relevant as well. So as you progress through this trust readiness level perspective, you can think about different people involved in this whole process. You can think about the issues of reliability, acceptability, and transparency throughout this whole process. And to get to the nine's the holy grail, right? You need to have shared perspectives across the community. So you might ask, has any technology ever reached a 9? In my view, the Air Force's Auto GCAS platform has reached a 9, where the community of users has such high trust of the technology, they absolutely endorse it. I would say that's actually what motivated me to put that 9 out there, was it's shared across the community. So I know it's possible, but it does take a lot of work. All right. And I think I left a couple minutes for questions, so I'm going to put my contact information up here in case if any of you guys ever have ideas, questions, thoughts about human-machine teaming. I'm always happy to have a conversation. So, thanks. I know it's early, so it's okay if you don't have questions.
What we're hearing here is kind of tension in some sense between testing and evidence and assurance that these technologies work well and getting things out to the field. So how are you kind of thinking about moving away from kind of full rate production decisions to software-enabled systems and kind of delivering them to individual units or for certain subsets or portions of mission sets? For these new capabilities that kind of need to do more learning in the field and getting a good sense of what they can and cannot do, especially with the real operators?
Yeah, that's a great question. I don't have a specific answer other than to say I think the rollout of technology is going to become more and more important the more complex you give the more complex the software is. So software is going to be rolled out in a first increment. There's going to be lots of refreshes, updates to those things. We need to have the infrastructure that supports that from a plain old like software infrastructure perspective. We also have to have the expertise at the unit level to integrate those things. And I would say to really understand the implications of new rollouts as they unfold. So did this upgrade just break what we were using it for yesterday, right? Those sorts of things. And I think that might require potentially rethinking some of the unit structure. Is there a particular software-centric position you need to create in those sorts of units?
Great, thank you.
Hey, Laura Freeman of Virginia Tech, longtime test and evaluation enthusiast. And one of the things that we see all too often in operational tests is that human machine teaming was not necessarily taken into account in the design of these systems. And so from a test perspective, it gets depressing to observe over and over again that the system was not engineered with this human machine team in mind. What are things from your perspective that the DoD can do to better build that into the acquisition process, especially in this context of going faster? How do we make that a more institutional practice? Thanks.
That's a great question, and I completely agree with the comment. I see this myself as well, unfortunately. How do we fix this? I think we need to get human and machine teaming requirements into the acquisition process for design. It's a simple answer. That's not a simple way to implement that. So doing what we can to work with program offices to make sure those requirements are identified in the original design process. Yeah.
Hello, Frank from IDA. You were mentioning that there was one group that used a less performing AI system because it was more understandable.
Mm-hmm.
What were some aspects that made it more understandable in terms of some of the insights that you learned from that experience?
Yeah, so that's a great question. So in that particular case, the agents were designed to do some very tactical based behaviors. The tactical behaviors could be programmed in certain ways. Some of the ways that were more understandable were based on expert systems, as opposed to, technically they were hybrid systems. They used expert systems in combination with reinforcement learning techniques. They were a little bit more understandable because the expert systems based essentially their models on how the tactics were done today. Whereas the more reinforcement learning only based methods just used reinforcement learning, and their behaviors were less intuitive, we'll say. Does that make sense? Okay. Great. Well, thank you very much.